In the last video, we talked about transformations of random variables, that when we multiply the random variable by a constant, it affects both measures of center and measures of spread. But when we add or subtract a constant, it only affects measures of center and any other measures of location, like the minimum or the maximum point, but not measures of spread. The shape of the distribution will not change either way. Something I didn't mention was that this is true for both discrete and continuous random variables. So in particular, this is true for a normal model. So we have here a situation where we're going to rescale some test scores that are normally distributed. In a large introductory statistics class, the distribution of x equals raw scores on a test was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. Now don't be shocked and think everybody failed the test, that it was a test out of 100 points. My guess is it was probably a test out of 20 or 25 points, and this is the score. And the professor, though, wants to scale it into a larger amount of points. So the professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. So right now we have the raw scores, so the distribution of x, we have mu, so actually why don't we just say for x, we have a normal model with a mean of 17.2 and a standard deviation of 3.8. But we want to rescale the scores. So these are the raw scores. So with the rescaled scores, we are going to be multiplying x by 4 and adding 10. So the rescaled scores are 4x plus 10. So the question is, how does that affect the mean and the standard deviation then of the normal model used to represent the scores? So for our rescaled scores, mu of x would be the expected value of x. Actually, let's call the rescaled scores r. So r is equal to 4x plus 10. Or maybe I should call them y. I think I called them y before. Yes, let me call them y. Then it will match my notes that I've already printed. So the mu of y, or the expected value of y, is the expected value of 4x plus 10. Well, we learned before that measures of center are affected by both multiplication and addition. So this is just going to be 4 times the expected value of x plus 10. So it's going to be 4 times 17.2 plus 10, which gives me 78.8 points. So that's the mean. The standard deviation, or sigma of y, or the standard deviation of y, is only affected by multiplication. The standard deviation of 4x plus 10 is just 4 times the standard deviation of x, because the 10 has no effect on the I'm kind of crossing it out. I'll sort of cross this out. So even the 10 doesn't really affect it. Now, is it still the variable 4x plus 10? Yes, but the standard deviation is not affected by the 10. It's only affected by the 4. So this is going to be 4 times 3.8, which turns out to be 15.2 points. So we're dealing with a normal model that has a mean of 78.8 and a standard deviation of 15.2. So let's recall, kind of our 68, 99, 95, 68, 95, 99.7 rule. Okay, remember, 1 standard deviation away from the mean, 2 standard deviation, 3 standard deviation. So 1, 2, 3. Remember that, here's our center, that 1 standard deviation occurs about where the point of inflection, where it starts curving, going from concave down to going to concave up. I probably didn't draw it exactly at the right place, but pretty close. So this would be 78.8, and then we'd add 15.2 to that, and if we add 15.2, that would be 95, I believe. Let's see, 78 and 10 is 88, and 88 plus 5, I think it's 94 rather than 95. This turns out to be 94, and then you'd add 15.2 to that, and that would be 109.5 5, etc. And you could go down. I'm not really interested in the other ones because I'm interested now in the probability that x is greater than or equal to 90 points, because that's what it's asking me here, the rescaled score. So 90 would be about right here maybe. So here's 90. So I'm looking at this, and I'm just doing this just to remind you that about what this would be. Well, if this is 68% from here to here, then the remainder on either side would total 32%. So this would be 16% from this dotted line on over beyond 1 standard deviation. So I would expect this to be 20-some% probably. I'm just showing that just as a reminder of some things about the normal model. I'm going to do normal CDF and calculate the probability that in this normal model I get 90 or above. So 90, infinity, 78.8, comma 15.2. So that's our left bound, right bound mu and sigma, and that turns out to be about 0.23, which is about what I anticipated. So we have identified our model using the mean and standard deviation. We have shown the shaded region that we're trying to find. We have made the calculation of that shaded region, and now we want to write a conclusion. The probability that a randomly selected student would score .90 points or more is about 23%. Or you could say about 23% of the students would score 90 points or more. So there would be an example of a rescaled normal model. Just to show you the difference in the two models, here would be a normal model representing the original scores with mean 17.2 and a standard deviation 3.8. So notice has a very narrow spread, very tall. Here would be the model 78 with the mean 78.8 and standard deviation of 15.2. It's more spread out. Why is it so much shorter than the other one? Well, the total area under the curve always has to equal 1 for a normal model. So since this one is very skinny, it has to be a lot taller than this one that is more wide and spread out. But notice, changing the mean and standard deviation in a normal model does not change the shape. It's still a normal model either way.